Hi everyone! Long time no see, but I have an excuse for that. I wrote the core of the operating system in Zik and from scratch. And I also ported TinyC for my architecture. So why am writing my own operating system instead of using some existing one? To learn, to test my ideas, and to optimize it for my needs. Moreover, I want my OS to be general-purpose operating system, where users can run their own applications, like in Windows, or Linux, or your macOS, but on a microcontroller, which is domain for highly specialized RTOS solutions like FreeRTOS or Zephyr, except for micro-Linux, but this is different story. My main goal is to provide a system with a C compiler with POSIX compatibility, which can be used similarly to well-known Unix or Linux-based operating systems. With POSIX compatibility, I hope I will be able to easily port or just compile software that already exists. My operating system development is ongoing on the latest MSPC board in version 2, which means it contains RP2350. This MCU is a cheap beast in embedded world. Huge amount of RAM, over 500 kilobytes, and external flash up to 16 megabytes. Moreover, I can attach external PSRAM memory up to 16 megabytes connected to the internal bus, and my board is using that. I chose that my OS will be written in Zik language. Of course, it uses parts of assembly code, because it has to. Some parts must be written in assembly to reach a most possible control. Userland applications I plan to implement in C. Why? Because my goal is to run a C compiler directly on that machine. Not by using the standard way with cross-compiling code for microcontrollers. Wait! Are you going to run a whole C compiler on microcontroller? Yes, indeed. This sounds as a really interesting experiment. But in the past, C compilers existed for even more restricted devices. Zik? But why? Because it is something fresher than old friend C. Zik has awesome features, like compile time, where you can use their full standard library, integrated build system, package manager, and it is more safe than C. When I was using it, if something compiling, most probably is working, except logical bugs, of course. And since it is C-like language, it is simple without hidden control flow or hidden memory allocations. Thanks to that, it is a really expressive language that can be easily read and understood by anyone. Together with the OS implementation, I started porting the C compiler to support ARM version 8M architecture. To save the time, I decided to base on the already existing TinyC compiler from Fabrice Bellard. TinyC doesn't support thumb instruction set, but I was able to find some fork to help me start implementation of T32 instruction set inside TinyC compiler. Then I extended linker implementation to support global offset table together with PLT and basically the position independent code. I have decided to start parallel work on the compiler and the OS itself, so then I can use it from the start and adapt compiler for my needs. Right now, since the operating system lacks necessary system calls, I'm using it only as a cross-compiler, but in the future it should be possible to recompile that exactly the same compiler for my machine and run directly on it. But this will require one more feature to be implemented, which is YAV file format support. Currently, my TinyC fork produces ELF files exactly the same as GCC. And then I'm converting them to YAV files using Python script. More details about YAV file format is in the video about dynamic linker for cortex-m creation. TinyC compiler does not support text and data separation using base register. GCC has corresponding flag no peak data is text relative. So I can create a relocatable executable that uses shared libraries, but I can't share the already loaded text section of the shared library between many executables. Of course, this is possible in the TinyC compiler, but I need time to do it. This is going to be a dedicated video, but for now, it is fine as it is. Wait a second, did you say shared libraries running on MCU? Yes. I've even created a dedicated series of videos about the creation of YASLD, which is my dynamic linker for cortex-m microcontrollers. For the sake of the operating system, I've just ported that implementation to Zig language. Of course, with some small changes, but overall, it is exactly the same dynamic loader described in that separate series. So is my OS finished? Of course not. Does it have memory leaks? Possibly yes. Any unoptimized code? No, of course. Tons of bugs, missing features, lack of error handling. Let's be clear. I just implemented the core of the OS. Now it is time to transfer my code from this into this. Basically, this means adding more system calls, extending variants of already implemented ones, to get POSIX compatibility. And I have to implement Erno. Right now you have to guess what happened. Also some features like support for memory protection would be useful, more drivers, especially to support external memory and external keyboard. Those ones are to be covered in the future. Alright, let's walk with me through main pillars of my operating system. If any topic that will be covered is interesting to you, and you would like to get a separate video with details about it, then you can get it. Write a comment under the video about what you would like to see. I will select a few comments, I don't know, 1, 2, maybe 3, that are related to that topic with the most likes and prepare a video specially for you. I'm waiting up to 3 weeks from releasing that video. Okay, let's go. I started implementation from working on a build system. Main complex task was to create a sensible dependency tree for the kernel executable and hardware abstraction layer. This is my first project using Zig language, and the beauty of Zig is that its build system and Zig is the same. Build recipes are just Zig files, so while learning the build system, I was also learning Zig itself and its standard library. I decided to use PyKeyConfig for configuration manager. I like those keyconfig menu configurations, when you can select options that you need. PyKeyConfig allows you to add your own config generators, so I implemented a Zig generator. Thanks to that, I can easily integrate configuration into both build system and the kernel. For RP2350, I've used Pico SDK where possible. I found that UART implementation lacks volatile in one place, and LLVM using Zig generates an infinite loop in release builds. So I've re-implemented part of it using pure Zig. Having a way to abstract hardware support implementation, I started working on the RP2350 booting process to reach the first Hello World print. RP2350 has a more complex second stage bootloader than RP2040. It has support for security features, multiple flash partitions, try before buy feature. It seeks for especially crafted metadata blocks inside the flash memory to run your firmware. For a simple booting procedure from the first partition, image definition metadata is already provided in the datasheet. Thanks to Zik compile time magic, together with linker script, I can embed that block easily. In the future, I'm going to extend or maybe re-implement YasBoot as a bootloader for my OS. Right now, due to lack of it, I have to hardcode rootfs partition address. But it is fine for now. Speaking about rootfs, I've implemented virtual file system support inside my operating system using object-oriented programming. But Zik doesn't support object-oriented programming nor C. But of course you can implement runtime polymorphism on your own. You just need to handcraft the vtable. And I used pattern already used by some Zik projects to keep vtable and pointer to the real object as a separate structure. To allow mounting file systems, I've created a separate abstraction. Then I've implemented support for ROMFS and RAMFS file systems. ROMFS is read-only file system and keeps rootfs and userland applications, and other stuff needed by OS like includes, libraries. RAMFS keeps temporary files. It is like temp folder in Unix-based operating systems. Both supports execute in place, but execution from flash requires me to implement previously mentioned text and data separation in C compiler. Currently I'm running all applications from RAM memory due to that restriction. Next pillar of the operating system are processes. I implemented them to support parallel execution of many applications. The whole thing in basis is really simple. Just some periodic interrupt triggers context switch and replaces the currently running process. This is round-robin scheduling, but I modify that a little bit so processes might be interrupted and placed on the waiting list when they are waiting for some condition. For example, the underlying process called sleep, or it's waiting for some I/O like UART or keyboard. On RP2350 and also RP2040, it is possible to implement full symmetric multiprocessing, because they are dual-cores MCU. But it has one caveat. Without MMU, I can't change section of addresses of already loaded programs or libraries. Let's consider that program on a diagram. When a program stores pointer to heap memory on its own stack, for example, due to malloc call, then stack points to a fixed memory address, and heap cannot be moved somewhere else. The program becomes no longer position independent. To be honest, position independence in my case is only while loading code. When it is running, it is no longer position independent. So to run two processes in the parallel, I have no other idea than splitting memory in half and reserve chunks per process. Even if I'm using page allocators right now, which allows heap to be fragmented, if some process gets the same page as other already suspended, then I can no longer run them in the same time. Of course, splitting memory will limit memory that processes may use, but it should be fair for both processes. I am leaving the SMP topic for the future. For now, using a single core is fine. Processes have some code written in assembly. I have to dump registers on the process stack in a really controlled way, and also some other artifacts that must be restored when the context is switching. And restoration of process must follow exactly the same way, but in the reverse. The whole process must be fully controlled by implementer. Otherwise, funny things are going to happen, like random crashes, mixing data, hard faults from nowhere. Running processes simultaneously, even on a single core, requires a basic synchronization mechanism. For RP2350, which contains ARM version 8M, atomic operations may be implemented using LDREX and strx instructions. But RP2350 also contains hardware spin locks, similar to the RP2040. Right now I'm using hardware spin locks to implement semaphores. Since semaphores are used in user processes, its implementation triggers system calls to delegate operation to the kernel. But please keep in mind that RP2350 contains bug in CO spin lock implementation, which is described in RP2350 E2 errata. In the future, I may decide to change to ARM atomic instructions for RP2350. Right now I'm using SIO because implementation of my OS was started on RP2040, so it was easier to me to just move that implementation from RP2040 board. As I mentioned, I'm going to have a C compiler on board. Oh, one note. I'm going to add support for assembly language too. But right now I only added what I needed to trigger system calls from my libc. So this means that only 2 instructions were implemented in TinyC compiler. Having C compiler means that I also need libc. A C compiler without standard library is not really useful. Libc is highly coupled with the operating system and the compiler, so I decided to implement my own. Otherwise, I would need to create adapters to get compatibility, which of course reduces performance in both memory and time domains. Again, to save the time, I selected the most promising libc implementation, I forked it as a base, and then I extended with functionalities that I need. To do that, I chose need libc. It is not full libc implementation, so I will have to add missing features, but it is simple, and I need simple implementations right now to reduce work while fixing bugs in compiler and the OS. One note worth mentioning is that this libc is used by applications that are running in user space. Kernel uses newlib. Memory management is important too. My general idea is to separate the kernel and process memory. In the future, I will secure them using the MPU which RP2350 contains. So I've reserved memory for the kernel and processes in the linker script of operating system. Then I splitted memory for processes into 4 KB chunks. Process metadata is kept in kernel memory space. The reason for that is I don't want processes to be able to destroy or crash my operating system, but the rest of their memory lies in their dedicated space. So if they do something bad to their own memory, nothing happens because operating system keeps track what memory is allocated to which process. To demonstrate some real behavior and also for testing purposes, I've implemented a simple shell application, of course using C. Later I will be able to extend their features using only my board, together with some core utils like ls or cat. Alright, that's all for today. For the future, I think that priority is to add keyboard support and VGA card. Then after adding compiler, my board will be fully independent from the host. As I said previously, if you want some topic to be extended, then I remind you to write a comment under the video and vote for others' comments. As always, thank you for watching and see you soon.
Let's play some game.